Did you know there are data centers where the servers don't use fans at all? In fact, some servers are completely submerged underwater. Well, not exactly water, but a special engineered fluid. No air conditioners, no raised floors, no hot aisles, no cold aisles, no computer room air handlers. Instead, entire servers sit inside tanks of liquid while enormous AI workloads operate around the clock. At first glance, it looks completely wrong. After all, we've spent decades learning that water and electronics don't mix. So why would anyone intentionally dunk a $1 million server into liquid? The answer is simple. Artificial intelligence is changing everything, and traditional cooling methods are beginning to reach their limits. Today we're going to explain exactly what immersion cooling is, how it works, why AI is driving its adoption, and why it may dramatically change how future data centers are designed. Let's get started. For decades, data centers have primarily relied on air cooling. Cold air is delivered to the front of the server. The server fans pull that air through the equipment. The air absorbs heat. Then the hot air is removed from the room. This worked extremely well when server racks consumed 5 to 10 kilowatts. Then racks increased to 20 kilowatts, then 40, then 60. Today, many AI deployments exceed 100 kilowatts per rack. Some are approaching 200 kilowatts and beyond. At some point, air simply becomes inefficient. You can only push so much air through a room before energy consumption, noise, and infrastructure complexity become enormous. Moving air is difficult. Moving liquid is much easier. In fact, liquid can transfer heat thousands of times more effectively than air. And that's where immersion cooling enters the picture. Immersion cooling is exactly what it sounds like. Instead of cooling the room, you cool the servers directly. The servers are installed inside specially designed tanks filled with a non-conductive dielectric fluid. Dielectric simply means electricity cannot flow through it. The liquid safely surrounds all of the electronic components without causing short circuits. As the processors generate heat, that heat transfers directly into the liquid. The warmed liquid then travels through a heat exchanger where the heat is removed before the fluid returns back to the tank. Then the cycle repeats over and over again. Think of it like placing a car radiator directly around the entire server instead of trying to cool it with room air. There are two primary types of immersion cooling: single-phase immersion cooling and two-phase immersion cooling. Let's start with single-phase. Single-phase immersion cooling. This is currently the most common approach. The dielectric fluid remains a liquid at all times. The fluid absorbs heat from the servers. Pumps circulate the warm fluid to a heat exchanger. Heat is removed. Then the cooled fluid returns back to the tank. Simple, reliable, and relatively straightforward. Now let's look at two-phase immersion cooling. Two-phase immersion cooling. This is where things get interesting. The dielectric fluid is designed to boil at relatively low temperatures. As the processors heat up, the liquid begins to boil directly on the server components. That boiling creates vapor. The vapor rises upward. It contacts a condenser located at the top of the tank. The vapor cools, turns back into liquid, then drips back down onto the servers. No pumps are required inside the tank itself. If that sounds futuristic, that's because it is. You're essentially creating a miniature weather system inside every server tank. So, what does the equipment look like? Imagine a large bathtub with a lid. Inside that tank are server blades mounted vertically. Technicians can open the lid and remove individual servers for maintenance. The tanks contain fluid distribution systems, heat exchangers, monitoring sensors, temperature controls, and connection points to the facility's water loop. Interestingly, because there are no server fans, the environment becomes dramatically quieter. One of the loudest components inside traditional servers simply disappears. A common misconception is that immersion cooling eliminates mechanical cooling systems. It doesn't. The heat still has to go somewhere. The only thing that changes is how we capture the heat. The heat still ultimately leaves the building through mechanical infrastructure. That may include chilled water systems, dry coolers, cooling towers, fluid coolers, or other heat rejection systems. The difference is that we're transporting heat with liquid instead of moving enormous amounts of air through a room. In many ways, immersion cooling simplifies portions of the data hall while shifting more emphasis onto facility water infrastructure. This is where things become very interesting from a construction standpoint. Many things we've traditionally associated with data centers may become less important. Hot aisles, cold aisles, perforated floor tiles, massive overhead air distribution systems, entire rows of CRAH units. Some facilities may eliminate many of these components altogether. Instead, you'll see rows of immersion tanks connected to fluid piping networks. In many cases, the building begins to resemble an industrial process plant more than a traditional data center. This is one reason mechanical engineers are becoming increasingly important in AI facility design. So why are companies investing billions into this technology? There are several reasons. First, significantly higher rack densities. Second, improved energy efficiency. Third, reduced fan energy consumption. Fourth, quieter operation. Fifth, potentially smaller data halls. And sixth, the ability to support next-generation AI hardware. Perhaps one of the biggest advantages is consistency. Every electronic component experiences nearly identical cooling conditions. There's less concern about hot spots forming inside the server. But immersion cooling isn't perfect. There are challenges, the fluids are expensive, technicians require specialized training, maintenance procedures are different, server compatibility must be considered, the equipment ecosystem is still evolving, and the entire industry hasn't standardized around one approach yet. This isn't simply taking a traditional server and dropping it into a fish tank. Everything must be engineered for this environment. 5 years ago, immersion cooling was considered a niche technology. Today, AI has completely changed the conversation. Every time larger AI models are released, more computing power is required. More computing power creates more heat. More heat demands new cooling solutions. The race to build AI infrastructure is forcing engineers to rethink decades of data center design assumptions. And immersion cooling is becoming one of the leading solutions. We're essentially witnessing the birth of an entirely new generation of data centers. So, let's summarize. Immersion cooling does not cool the room. It cools the servers directly. Servers are submerged inside a non-conductive dielectric fluid. Heat transfers into that fluid. The fluid carries the heat away. Then facility mechanical systems ultimately reject that heat outdoors. As AI continues pushing rack densities higher and higher, immersion cooling may become one of the defining technologies of the next generation of data centers. And perhaps the strangest part of all, the future of computing may involve intentionally putting our most expensive electronics into a bathtub full of liquid. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.